Hi everyone, my name is Yonglong. Today I'm gonna talk about many-body correlation in magic angle twisted bilayer graphene. This work was done in Professor Ali Azani's lab at Princeton University. Let me start by acknowledging my collaborators. The first part of my talk was done in collaboration with Berthel, Xiaomeng, and Cheng Li. And the second part and the ongoing work is led by Dylan, Kevin, and Muncho using a new STM that Sanjay has designed. All these, as I said, happened in the Yazdani lab. And the theoretical support was provided by Bill and Andrei Bernavik. And as usual, BN Crystal comes from NIMS. And we are very grateful for support from various funding agencies. Since the previous speaker has done a really good job in presenting the background, I don't think I need to spend much time on this. So by now, experiment and theory together has shown that there is actually a rich set of phases in magic angle twisted bilayer graphene, starting with a correlated insulator and superconductors. And more recently, there's experiments showing signature of ferromagnetism together with intrinsic quantized Hall conductance at zero or moderate magnetic field. And what I'm going to tell you about today is what we can learn using a scanning tunneling microscope. Specifically, I'll start by presenting experiment that visualize the magic angle Y devices. And by performing spectroscopy on these devices, we can actually learn pretty quantitatively how correlated are the electronic states in this system. Then I'll report the striking observation of cascades of transition as a function of filling, which now we understand as a result of the interplay between the quantum degeneracy, namely the spin and Vallée, and the interaction in the system. And towards the end, I will present some preliminary experiments on the possible superconducting states. So we make the sample using the standard TN stack in-house. The only difference is that because we need the electron to tunnel from the tip to the sample, this sample, they don't have top BN. This is just a nice image that I want to show, showing that the STM tip is approaching the sample. So if you do everything correctly, what you will see if your tip is landing on the twisted bilayer graphene is this moire pattern. The bright yellow spots are associated with the region where the first and the second layer graphene are in the AA stacking fashion, and these dark regions correspond to the AB stacking region. If you take a spectra on the AA side, what you will see is two very pronounced peak in the tunneling density of state, and then the tunneling spectra. And then this is exactly the signature of the flat band, the Van Hall singularity of the two low energy flat bands you would expect, for example, in the simple continuum model. But if you look very closely, the peak width in the spectra and also the separation between the two Van Hall singularity are actually larger than what you expect from the original McDonald model. And what we can do is actually to use the STM to characterize the local structure more carefully. And then what you see is that the first thing you see is that the moire wavelength is not isotropic, meaning that there's the presence of the string in the sample. And by using a uniaxial string model, you can actually find the molecular value for the twist angle as well as the strand and the direction of the string. And by analyzing this topograph, we can also extract the value of the lattice relaxation, which is the ratio of the area between the area of AA side over the AB side. And if you do all this, we can use this experimentally extract the value and then feed them back to extend the original continuum model to take into account the influence of these two. And if you do that, what you see is that the flat band now, color in blue, acquire additional bandwidth, and we can calculate the local density of state from the model. And what we've now we find a reasonable agreement between the measured spectra and the model. And what we find is that the bandwidth of this flat band is around 10 milli-electron volt, and the gap that separates the flat band, the remote band, is around 15 electron volt. The bottom line of this is that if the flat bands are full, this single particle picture works pretty well. Now, things would become more complicated and also more interesting if you tune this flat band across the Fermi level. Here, what I'm showing is basically the tunneling spectra as a function of gate voltage. Previously, the line trace is just a cut from this 2D plot. The color tells you how large the tunneling tunneling conductance is. Let me divide this complicated plot into 3 different regions. So in region 1, what we have is both of the flat band are being filled. So if you try to remove electron, what you will see in the tunneling spectra is that it just rigidly moves towards the Fermi level. The same also can be found for the region 3, where both of the flat bands are above the Fermi level, and then they you just see a rigid shift. If you look really, really closely, what you can see is that the field states, the peak width, actually gets sharper as they approach Fermi level. This can be well understood as the E-square behavior that you would expect from Fermi liquid theory. Now let's turn to the region 2, where things look messy. To do that, I'm going to show individual spectra of this region, and this is what it looks like. At first, you might want to look. You might be looking at the region around the Fermi level, where transport has shown correlated insulators, etc. And then in the spectra, we do see perhaps some gap opening and then closing. But what really caught our eye in this data is this abrupt broadening, as I outlined it here with the shaded region. What I meant is that, look, as soon as this flat band overlap with the Fermi level, the other flat band that's away from the Fermi level suddenly get broadened. And this broadening persists for all the filling factor, not just the integer filling. Similar behavior is also found when you look at the spectra where the lower flat band crosses the Fermi level. This is quite striking because it's quite rare, and to my knowledge, maybe very few, no system would exhibit such a behavior. When you try to move a band across the Fermi level and then the other band suddenly just get broadened. So how can we understand this? The first thing we have tried is to model the interaction by Hartree-Fock. For this, we make no assumption about the symmetry breaking, meaning that we will just put in the mean field term and then let the system solve the system self-consistently. And the left panel is the calculation result to be compared with the experiment. What you can see is that in the calculation, even though there might be some gap opening, but the peak width for the band that's away from the Fermi level remain essentially the same, in contrast to our experimental observation. So this means Hartree-Fock cannot really capture what we see in the experiment. And why does the mean field picture fail? To give you an idea of this, let's consider the simplest model that you can imagine, just 2 atomic level that's separated by 2 epsilon, and to mimic the separation between the 2 flat band and the real system. And now, if I don't have any electron, then the cost or the possibility of adding electron would be just 2 Lorentzian peak centered around epsilon and minus epsilon. And if you have 1 electron occupying the lower level, then the cost of adding an electron in the upper level would be shifted by the on-site interaction U. Now, in the case of a fractional filling, P, what mean field tells you is that you're going to approximate this fractional filling as a P electron. And the cost for adding an electron to the upper level would simply be P times U. But we do know that this is not physical because the number of electrons is integer, cannot be a fraction. So the meaning of a fractional filling P in a strongly interacting system is actually that you have probability of P having 1 electron and probability of 1 minus P having 0 electron. And then if you take this probabilistic picture, what you see is that you will have 2 peak which broadens the spectra. What this means is that we need a model that can faithfully take the interaction into account without making any assumptions. So to do that, we're gonna use the extended Hubbard model. And a lot of theory work have shown that even though the Wannier function are centered on AB and BA side, but the maximum charge density is actually centered on AA side. In the STM experiment, we do see that the spectrum weight of the flat band is centered on the AA side. So for the Hubbard model, we're gonna use triangular lattice. For each side, we will have 2 orbitals. Each orbital will only have 1 single flavor. And then we will consider not only the on-site interaction, but also nearest neighbor interaction between sites. And then the approach we're going to take is just to do the exact diagonalization so that we can take into account this charge fluctuation because of the strong interaction. Here's the results from a 7-site cluster. What we found is that the 2 peaks, once you have one of the flat band overlapping with the Fermi level, the other flat band suddenly split into 2, what we call broadening. This is limited by this is because of the single flavor of the orbital. But now you see that such a broadening do persist no matter what filling factor you are at, and this captures the experimental observation pretty well. And from this, we track the on-site interaction to be 30 millivolt, which is the largest energy scale in the system. Similar broadening is not only seen in our group, but is also present in the data from other STM group, meaning that this is a robust result. Now, if you look at, you have stare at this data long enough, as I did, you might notice that there are actually some peculiar or finer feature starting from the Fermi level and then extend for some time and then it disappear and then another copy repeat and all. And at that time with this quality, I was not really able to convince myself that this is real, not convincing my advisor. But I should mention that this experiment was done on a sample that has some contamination, this little contamination, yet we were able to find clean enough patches to perform the experiments. Since this experiment, a lot of effort has been devoted to improving the sample quality for this TBG devices. And by now, these 3 gentlemen, they are now able to make devices that are super, super clean, as you can see here. And these devices that now they can make are at least a few hundred nanometer contamination free and with minimal strain. And this coded number is essentially bounded by how much time they want to spend on taking the topograph. So this is really a major step. Now, if you repeat the same experiment on these ultra clean devices, you can now clearly see a cascade of changes in the raw spectra. Because there's large variation in the density of state, we can normalize each curve by the I over V. And now you can even more clearly see these fine features. These fine features repeat in 4 evenly spaced intervals for the before the chemical potential is tuned to the charge neutrality point. And after that, you get another 4 for the lower flat band, as outlined in this sketch. So specifically, if you look closely to this data, for positive bias, each unfilled excitation appears first at Fermi, then disperse outward to energy of about 23 millielectron volt before disappearing. And I should say that these cascade features are extremely robust and highly reproducible for magic angle devices as exemplified by this additional data set. So how can we understand this? The fact that we see cascades feature highlights the importance of the fourfold degeneracy in the system. In the ideal case, one should formulate a full model that has hopping on-site interaction with all the spin and Valet flavors. But the problem is such full model would have too many degrees of freedom, and it would be impossible to solve this exactly. So instead, we use the simplest model to take into account the influence of the flavors. Specifically, we're gonna have 2 orbitals. Each of them can host 4 flavors, and we will assume that there's no hopping, and then try to calculate the addition and removal spectra as we did in the first part. So the result of such model is displayed here. The x-axis is the energy, and the y-axis is the filling factor, and the intensity tells you the spectrum weight of the possible excitation. So what you see here is that at each integer filling, there are sudden jumps, and then there are excitations that emit from the Fermi level and then persist for some time, which looks very similar to the experiment. In this model, the on-site interaction separates this fourfold degenerate flat band into 1, 2, 3, 4 subbands. And if now we associate this feature with the experiment, we can actually extract quantitatively, again, the on-site interaction more accurately, which is of the order, which is around 23 millielectron volt. Now you might criticize that in this model, the shift is sudden and then it's very rigid. Whereas in the experiment, you see this excitation disperse and then come back. We can actually do a better job to improve the model by adding a small hopping between the sites. Here, I'm showing the results of a small cluster exact diagonalization with a finite T, but still maintaining a very large U. And now what you see is that this feature indeed starts to disperse as you change the filling factor, which is even more consistent with the experiment. So in this vanishing hopping model, if you look at the chemical potential of the system, the chemical potential is expected to exhibit discrete jumps wherever the system hits the integer filling. Now the question is, can we measure something related to this with our experiment? So to do that, let me first remind you, in twisted bilayer graphene, you have this AA stacking region and AB stacking region. And the band structure calculation show that the flat band has a very strong spectrum weight on this AA side, whereas AB side would be more sensitive to the remote band electron. The remote band electron are delocalized. So what that means is that if you take the spectra on AB, then you can obtain information that's more sensitive to the delocalized electron and their interaction with the flat band. Therefore, could provide a way to measure the chemical potential in the system. This is the data taken, similar data taken on the AB side. I want to point your attention to the onset of the conduction remote band. You can clearly see that the onset energy exhibits a series of oscillation. And the same holds, even though it's less clear, for the valence remote band. So to better present this, we can just extract the onset energy as a function of gate voltage as plotted here. And you see clearly this oscillation. So in order to understand this or to relate this to the chemical potential, one can make a simple model as the following. So the onset of the remote band energy can be described by the sum of several terms. The first term would be the single particle gap that separates the flat band and the remote band. Second term is the mean field interaction between the electron in the remote band and those in the flat band, and then the chemical potential. And if you do this, then you see that the chemical potential increase very fast and then exhibit a cusp and then increase very fast, and such a behavior repeats for all the every time you hit the integer filling factor. So I should mention that similar results has been obtained by Shah Ilani's group at Weizmann Institute using the compressibility measurement technique, and you can see in their case, the chemical potential also exhibit a cusp every time the system reached the integer filling factor. So now, having this in mind, if you look at the data more carefully, the cusp in the chemical potential forms at the junction of two asymmetric slope of the mu. This is consistent with the density of states at the top and the bottom of the Hubbard subbands. What this implies is that there is a sudden drop in the compressibility and the cyclotron mass, which can actually maybe explain why in the Landau fan measurement there's a strong asymmetry, meaning that the Landau fan only always pointing outwards with respect to the charge neutrality point. Now, having shown all this strongly correlated feature, one question that one might ask is, are these strong correlated features something special for samples that are at the magic or near the magic angle? To address this, we can simply repeat the same kind of experiment at other angles. And here's what you see. For both sample below the magic angle and above the magic angle, the cascade features are now gone, essentially gone. And this is actually very expected because if you calculate, the calculation show that the bandwidth is very sensitive to the twist angle, and then and also as soon as you deviate from the magic angle, the interaction strength would also go away. Therefore, there's no more visible, well-defined Hubbard subband. And I should comment also on the fact that these samples are sitting on silicon oxide, meaning that the sample is 300 nanometer from the gate. if you follow the analysis in this paper, then that would correspond around 23 million electron volts in great agreement with our experiments. So what are the consequences of this? So in our data, we show that when you are at the magic angle, the on-site interaction U is really the largest energy scale in the problem. And then this cascade of transition is a result of the interplay between interaction and the quantum degeneracy of the problem. And it's, of course, possible to have spin and valley polarized ground states at this integer filling. But with such strong interaction, the system could also break other symmetry than spin and valley. And we would need more experiment to determine the true nature of these insulators. So for the remaining time, I'll present some ongoing work in the Yazdani lab in hope about the superconducting and insulating ground states. So this work is again done by Dylan, Kevin, and Muncho. And once you cool down the system at the millikelvin, the lowest possible that we can reach in the lab, the spectra now develops gaps and a lot of finer feature at this low temperature. So I will be focusing on the lower flat band, where the spectroscopy can be most clearly associated with the transport experiments, and also where the transport experiments appears to show more robust superconductivities. So here, if you zoom in the data very close to minus half filling, what you see is that there is a gap that's forming plotted here of the size of 2 delta equal 2.4, then it quickly closes, then reopen. So this could be the possible insulating gap. And then if you go to the, if you dope beyond minus half filling, what you see is that here is a line cut cutting here. What you see is that there is a V-shaped gap appearing, and then if you fit it, the gap size is around 2.7 milli electron volt. And if you compare it with the BCS theory, taking the critical temperature as 1.5 from the transport, what you see is that the 2 delta over KBT ratio is extremely high, reaching around 20. Which means that if this is truly a superconducting gap, then it would be highly unconventional. And also you see this unusual nodal gap feature. With this, I would like to conclude. With our experiment, we find that U is really the largest energy scale when the sample is at the magic angle, much larger than the bandwidth. And because of this, charge fluctuation broadens the apparent gap. And together with the spin and valley degeneracy, the system split into a series of Hubbard subbands and other finer features. And we also see cusps in the chemical potential. Now there are a lot of remaining questions. Some of them are whether these split band would give rise to spin and valley polarized insulators, as well as what would be the nature of the superconductivity in this system. So with this, I would like to thank you for your attention.
Thank you very much, Yonglong. Okay, now we have time for some questions.
Can I ask a question? So when you're talking about the bandwidth, the ratio of the bandwidth to interaction and how it looks close to the magic angle and so on, do you compute it with or without strain?
It's with strain. The first part is with strain, and then I do believe that there is strain is always present in the system, and it's.
But in the later part, when you showed this very strong peaking of the band, like when the ratio of U over T So maybe you can go back a few slides.
Here?
Yeah, here.
Oh, this is the calculation from one of the reference, just to illustrate the point that the ratio of U over T would change when you go away from the magic angle.
But this one is without strain.
Oh yeah, sure.
So the ratio would be, in the realistic case, it will be still U over T, like W over U would be larger than what they have there. So you have 15 versus 23, that's like half.
10, yeah, 23 over 10.
Yeah, okay.
Yeah,
yeah so it's 2, okay.
Yeah.
All right, if there are no further questions, let's